Today we are going to take up the MOSFET characteristics. We need to plot the transfer characteristics and the output characteristics. The output characteristics is also called as drive characteristics. That means the drive characteristics, that is the output characteristics, and the transfer characteristics put together is called the static characteristics. So the aim of the experiment is to plot the static characteristics of the MOSFET. Okay. So the operators that is required is the MOSFET characteristics study unit. Basically, the MOSFET characteristics study unit has a MOSFET and a series resistance which works as a load, and there is one power source. So this power source I am calling it as V1, and for powering the gate and source there is one more power supply. I am calling that as V2. You can observe that both the power supply for the gate as well as the power supply for the load which is connecting to the MOSFET, that is through the drain and source of the MOSFET, have the rating of 0 to 30 volts. You can also observe the rating of the voltmeters and ammeters that have connected. 0 to 200 volts meter we are using for measuring the voltage across the MOSFET. Similarly, we are measuring the voltage across the gate to source through a voltmeter having the rating of 0 to 20 volts. You can observe that the voltage rating of the gate to source is less when compared to the voltmeter rating of the meter that is connected across the drain and source. Anyway, as far as this particular setup is concerned, both the power sources are having the same rating equal to 30 volts. And as far as the ammeter is concerned, you can observe that the maximum rating of the ammeter is 2 amps. One more fact is that all these voltmeters and ammeters are all DC voltmeters and DC ammeters, which is very much obvious as because we are using the regulated power supplies for conducting the experiment. Let us see the procedure for conducting the experiment. That is, the first part of the experiment is to conduct the transfer characteristics of the MOSFET. Let us see the procedure. As I told you, that transfer characteristics is also called as transconductance characteristics, and the output characteristics is also called as drive characteristics. First, we will start conducting the transfer characteristics or the transconductance characteristics. The procedure. What is the procedure? Make the connections as shown in the circuit diagram. First, we need to connect the voltmeters, ammeter according to the circuit diagram that is shown here. And then initially we need to keep V1 and V2 to a minimum. And as soon as we start the setup, there will be some minimum voltage that is present, which is presented by this power source. Similarly, there will be some minimum voltage that is presented by this voltage source V1. And next, we need to set V1 is equal to 10 volts. It has been mentioned that V1 is equal to VDS1. Means the voltage across the drain to source is equal to 10 volts. You can observe that if we don't give the proper gate to source voltage, which means that we have not made the MOSFET turn on into conduction, you can see that the MOSFET is in off state. So it is basically the connections between drain and source is an open circuit. which means that the current through the load and the current to the MOSFET, this entire circuit is an open circuit, which is indicated by 0 amps in this particular ammeter. Since no current is flowing, this particular point, that is the drive of the MOSFET, if you observe the circuit, is same as the positive of the input power supply. Similarly, the source of the MOSFET is same as the negative of the power supply. Thus, you can observe that the voltmeter will show the reading equal to the supply voltage. So we have to adjust the supply voltage such that this voltmeter shows 10 volts. Means we have adjusted the voltage equal to 10 volts. Now, we need to note down the current through the drain, that is ID, and the voltage between gate to source, that is VGS, for every zero point 0.5 volts increase in gate to source voltage, and that we have to enter in the tabular column, which is being shown here. If you see here, you need to increase the voltage between the gate to source step by step in the increments of 0.5 volts and observe the current through the switch, that is the drive. So, and if we come to the circuit diagram, you can see that I'm going to increase the voltage between gate and source indicated by this voltmeter step by step with an increment of 0.5 by using this potentiometer, which is used for measuring the varying the voltage of this source V2. Now, for every zero point 0.5 volts increment in VGS, that is the voltage across the gate to source, I am measuring the current through the drive. That has been shown here in the tabular column. And at the top, you can see that V1, that is voltmeter across the MOSFET, also called VDS1, means for a particular first iteration, I am calling it as VDS1, and second iteration, I am calling it as VDS2. So for the first VDS1, I will adjust the voltage such that it is equal to 10. And for the second set of readings, I will make it as equal to 1. I will increase the voltage to a different value and take the same readings. That is, I will increase the voltage between gate to source in steps of 0.5 volts and take the reading of current to the drain. That is ID in milliamps. And if you go on increasing the voltage between gate to source, there is a particular voltage which is called the threshold voltage indicated by VGS threshold, above which the MOSFET starts to conduct. If the voltage across the gate to source is less than VGS, very small leakage current flows. If it is more than that, then the current starts flowing. And if you further increase the gate voltage greater than the gate to source threshold voltage, then the drain current depends upon the magnitude of the gate voltage. So, which has been indicated. The same tabular column has been shown graphically, where the y-axis the drain current is indicated and x-axis the voltage between gate to source is indicated. You can see that till the threshold voltage, the current to the MOSFET is 0, indicating the MOSFET is in off condition. And once you cross the gate to threshold voltage, the current slowly increases to the MOSFET, and then the voltage across the gate to source gets clamped. With the increase in the supply voltage across the gate to source, you can see that the voltage across the gate to source remains constant, whereas the current goes on increasing, which is proportional to the amount of voltage that you supply to the gate to source, keeping the voltage across the supply, which is powering the load, constant. So this is the first characteristics. The same thing is there for the second set of readings for a different input voltage. You can observe that if I increase the supply voltage, the gate voltage at which it conducts becomes less. So for a lower voltage, for a lower supply voltage, let us say 10 volts, this characteristic is going to appear. And if you increase the supply voltage from 10 to 12, you can observe that the gate to source threshold voltage will jump back. That means it will start conducting at an earlier place where the gate to source voltage is much less than the previous one when the supply voltage was equal to 10. If you increase it to 12, then it starts conducting much in advance. So these two are the graphs that we can obtain. It is ideal graphs that we are obtained based on the above experiment. Similarly, we can conduct the drive characteristics, also called the output characteristics. For that, initially we need to set V2 equal to VGS1, that is 3.5. So for this experiment, we need to fix this voltage equal to threshold voltage or maybe a little bit more than threshold voltage. And then we need to concentrate only on this power circuit. I can say that this is the power circuit where the main voltage source is there, the load is there, and it is connected to the drain and source back to the source. It's called power circuit, and we are going to control the current through that power circuit by applying the firing angle, or you can say by applying the gate pulse between gate to source. It's called control circuit. So here in this particular drive characteristics, we are fixing this drive to gate to source voltage equal to 3.5, and slowly we are varying V1, and we are noting down the drive current, that is current to the MOSFET, and the voltage across the MOSFET. If you observe, so we need to keep this 3.5 initially, and for the second set of readings we can little bit increase, maybe 4.5, and take the same readings, that is voltage across the switch and current through the switch. We know that whenever the MOSFET is in on condition, ideally the voltage across the drain to source must be zero. Since it is a non-ideal device, we can expect some voltage to be present across the drain to source. And as we are increasing the supply voltage, we are expecting the voltage across the drain to source constant, if not zero, constant, or even if it varies very much marginally till a particular point of time, till a particular value of the supply voltage. After that voltage, the current starts saturating, means the current remains constant irrespective of your your effort in increasing the supply voltage. Even if the supply voltage is increased, the voltage across the drain to source, that is voltage across the switch, starts increasing, which results in the current through the switch becoming constant. That is what is indicated in this diagram. Like if you conduct the experiment for a very low value, just above the threshold voltage of 3.5, you can see that the current starts increasing linearly, and as you increase the supply voltage, ideally, we are expecting the voltage across the drive source to be zero, but since it is a non-ideal device, we are expecting some small voltage across the drive to source with an increasing current. And I am increasing the current, and correspondingly, the voltage across the drive to source is also increasing linearly. And you will reach a particular region where if you try to increase the supply voltage, you will see that even the voltage across the switch also starts increasing, and you will see that the current remains constant. So only between this region to this region, it's called linear region, where we are interested in operating the MOSFET as a switch. Once the operating region enters to this area, we are not interested in the operation of the MOSFET as a switch. Only this particular linear region is used for the MOSFET as a switch. The same thing is applicable for two different values of gate voltage, VGS2, VGS1, where VGS2 is more than VGS3 and VGS1 is more than VGS2. You can see that the current, the exact voltage, or you can say the current at which the drain current reaches the saturation becomes higher as you increase the gate to source voltage. So this particular graph is called the drain characteristics or the output characteristics.